Welcome back to sequence and series. We shall continue to tackle some more problems on this topic. Here is your first problem in this lecture. You drop a ball from a meters above a flat surface. Each time the ball hits the surface, after falling a distance h, it rebounds a distance RH, where R is positive but less than 1. Let me repeat the given information. You drop a ball from a meters above a flat surface. Each time the ball hits the surface after falling a distance h, it rebounds a distance RH. Find the total distance the ball travels. Up and down. Find the total number of seconds the ball is traveling. Assuming A, the height, is equal to 4 meter. Let us try to solve this problem as follows. The crux of the matter is whenever the ball travels a distance h and hits the surface, it will rebound from the surface to a height RH. Recall that first the ball is being dropped above a flat surface with a height a meters. So, this height is a. From this point you are dropping the ball. So, it will travel a distance down. Once it is on the floor, then it will rebound. If it travels a height h to hit the ground, it rebounds us to a height RH. So, since it travels first through a distance a meters, it will rebound to a height RA. And then it will come down traveling RA distance, right, and it will rebound. Since to come down it travelled RA distance, it will rebound the distance r square a. Up, it will come down the same distance and then rebounds r cube a, and so on. First it is dropped from a height of a distance. So, it travels down a distance, it hits the floor, it rebounds us. How much it rebounds us? It depends upon how much it travels to come down. Since it is a, it will rebounds to a height r a. Once it rebounds, same distance it covers down and then rebounds us r times the distance it travelled down way, which is r square a, and so on. So, the total distance will be, let me denote it as S, will be the first a height travelled down plus rebounds up r a and then down r a plus rebounds up r square a, then same distance down r square a, and so on, which will be a plus 2ra plus 2r square a plus etc. Now, if you see the second term onwards or second sum and onwards in this infinite sum, it is a GP. 2ra, 2r square a, 2r cube a, etc. is a GP with the first term 2ra and common ratio r. GP with first term 2ra and common ratio r. Given r is positive and less than 1, so this infinite sum is in fact convergent, and sum to infinity of a GP with the first term a and common ratio r is given by the formula a by 1 minus r, which we developed in previous lectures. Therefore, the required distance is a plus, the remaining is a GP with the first term 2ra, common ratio r. Therefore, sum to infinity of that GP is 2ra by 1 minus r. So, once a is given, we can find the value for the total distance. Second part of the question demands you to find total number of seconds the ball is travelling. Here we shall recall the law of motion. S is equal to ut plus half at square, freely falling body. So, acceleration is acceleration due to gravity, initial velocity is 0, therefore, S equal to half gt square, giving the approximate value of g as 9.8 meter per second square. This is 4.9 t square. So, once we know what is S, the total distance covered by the ball, we can isolate t as follows: t equal to square root of S by 4.9. In fact, to get a value for S, we need a and r. Second part of the question tells you a equal to 4 meters, r is not given. So, we will get t in terms of r. This solves the problem. Here is yet another for you. Can you make an infinite series of non-zero terms that converge to any number you want? The question is interesting for the following reason. First, note that in contrast to a finite series or a finite sum, an infinite sum may not have always a finite value. In rigorous language, an infinite series of real numbers may not be convergent. As we remarked in our previous lectures, even if we know by some way or the other that an infinite series is convergent, finding sum of an infinite series may not be that easy. In other words, a formula like sum of an infinite terms of a GP may not be available for an arbitrary infinite series. So, in our attempt to make an infinite series of non-zero terms that converge to some number, say L, we will try to confine ourselves to geometric progressions, for the obvious reason that for geometric progression we know condition for convergence and we know the sum of infinite terms of a geometric series in case of convergence. Keeping this in mind, let L be a given number. You are asked to find some series which is convergent, infinite series, and the sum of that series should be equal to L. Let us search the series in the domain of geometric series. Let A, AR, AR square, etc. be a geometric progression therefore, A plus AR square plus etc. would be a geometric series and it is convergent for mod r less than 1. In case of convergent, that summation a r power n minus 1 n equal to 1 to infinity is a by 1 minus r. What we are required to find is an infinite series whose sum is L given number. So, let us assume that the series is geometric series. So, we need A by 1 minus R to be equal to L, where for the time being restriction of R is that mod R is less than 1. So, to get a geometric progression and a corresponding geometric series with the sum as L, only condition is that A by 1 minus R should be equal to L with R some number between minus 1 and 1. So, there is only one condition, but for determining such a geometric progression you need first term A and common ratio R, two unknowns are there. First fix R some arbitrary value between minus 1 and 1 and use this formula to get A. Thus, selecting R such that mod R is less than 1, say for instance R equal to half and A equal to L into 1 minus R, we get a geometric series, namely L into 1 minus R plus LR into 1 minus R plus LR square into 1 minus R plus etc. And the observation that we had so far says that this series will be convergent because we selected R less than 1 and greater than minus 1, and the sum of this series would be L. So, it is always possible to find an infinite series whose sum is given number L. For our convenience, we worked on geometric series. It is interesting to note that L can be positive, can be 0 or can be negative. If it is 0, our series reduces to the trivial series 0 plus 0 plus 0 plus etc. So, this is like a inverse problem where instead of giving you a geometric series and asking the sum, the question is, given some number, can we construct a geometric series whose sum is the given number? Let us proceed. You have a pattern of squares. First 4 of the squares in that pattern is given. Outermost square has area 4 meter square. Each of the other square is obtained by joining the midpoints of sides of squares before it. Find the sum of areas of all squares. So, you are given with a pattern of squares. Outermost square has area 4 meter square. How do you get the next square? That is by joining the midpoints of each side of the previous square. This pattern is continued. So, this will be your 5th square in the pattern, so on. This will be the 6th square in the pattern. You are asked to find sum of areas of all the rectangles. Only thing given is area of outermost square is 4 meter square. Let us solve this. Note that if a square has each side length a, the next square obtained in this pattern by joining the midpoint will have side length as follows. Remember, the outer square had side length a and this is midpoint. So, this distance is a by 2. This distance is a by 2. You have a right angled triangle here. Let me denote it as A, B, C. That gives you length of BC, for which you can use Pythagoras theorem. BC will be square root of AB square plus AC square, which gives you a by 2 square plus a by 2 square. That is this is the main observation in this problem. If you have a square with the side length a, the next square in our pattern will have side length a by root 2. Next will be having side length a by root 2 by root 2 and so on. Whenever we have square of side length x, the immediate next to it in our pattern will have side length x by root 2. Therefore, corresponding areas would be a square, a by root 2 square, a by root 2 by root 2 square and so on. That is a square by 2, a square by 4 and so on. We are asked to find sum of areas of all the rectangle. That is, we have to sum these numbers. Therefore, sum of areas equal to a square plus a square by 2 plus a square by 4 plus etc. It can be easily observed that this infinite sum corresponds to a geometric progression with first term a square and common ratio 1 by 2. So, the sum would be first term by 1 minus common ratio. Since the common ratio is less than 1, in fact, it is convergent, and that is how we could write a finite value for that infinite sum, which amounts to 2a square. It is given that the outermost square has area 4 meter square. So, a square is 4 meter square. A square equal to 4 numerical value. Therefore, sum of areas is equal to 2 into 4, which is 8. with the unit 8 meter square. Basically, it is a problem on GP. Let us continue. Second term of a GP is 1000 and common ratio is 1 by n, where n element of n. Let Pn be product of n terms of this GP. If P6 is greater than P5 and P6 is greater than P7, what is sum of all possible values of n? A careful observation should reveal you that it is concerned with GP and product of terms in GP. Further, one term, I do not mean the first term, in fact here it is second term, is positive and the common ratio is 1 by n and n is natural number. Therefore, common ratio is also positive. If one term is positive and common ratio is also positive, then all terms of that geometric progression should be positive. That is one observation that may help us. Given Pn denote the product of n terms, therefore P6 is equal to product of 6 terms, first 6 terms, which is equal to P5, the product of first 5 terms into the 6th term. Let me denote the 6th term as T6. Tn denote nth term. So, P6, the product of 6 terms, is product of 5 terms, first 5 terms into T6. For brevity, we may add that Pn denote product of first n terms. Given P6 is greater than P5 and that implies T6 is greater than 1. Recall that all terms are positive and P6 is equal to P5 into T6. P6 is larger than P5. Therefore, P6 by P5 will be larger than 1, that is T6 will be larger than 1. Similarly, P7 is P6, the product of first 6 terms into the 7th term. It is given that P7 is less than P6. Therefore, T7 is less than 1. Thus, we observe that the sixth term of given GP is greater than 1 and seventh term is less than 1. The only information remains is that second term of this GP is 1000. So, let us connect this T6 and T7 with second term. Remember, a GP is of the form A, AR, AR square, AR cube and so on. Therefore, let me denote these things by first term, this is second term, third term, fourth term and so on. Let us connect every terms with the second term which is given to us. Note that the third term is R times the second term. Fourth term is R square times the second terms. Fifth term will be R cube times the second term and so on. Therefore, T6 equal to the sixth term equal to second term times how much it will be? R power 4. See this, third term is R times second term, fourth term is R square times second term and so on. So, sixth term will be R power 4 times second term and second term is given to be 1000. Similarly, T7 would be the seventh term, that is just a notation, which is equal to second term into R power 5, which is 1000 into R power 5. Thus, T power 6 greater than 1 translates to 1000 R power 4 greater than 1, and that is R power 4 is greater than 1 by 1000. Recall that the common ratio is 1 by n. Therefore, this implies 1 by n power 4 is greater than 1 by 1000. Taking reciprocal, this gives n power 4 is less than 1000. Using the second piece of information, namely T7 is less than 1, we get 1000 R power 5 is less than 1. That implies 1000 1 by n power 5 is less than 1. That implies n power 5 is greater than 1000. Thus, we are searching for value of n, all possible values of n, with n power 4 less than 1000 and n power 5 greater than 1000. It is not hard to see that n power 4 is less than 1000 if n is less than 6. You can think of fourth powers of 1, 2, 3, 4 and 5, which are all less than 1000. And it is not hard to see that fifth power is greater than 1000 only if n is greater than or equal to 4. Thus, we are searching for those values of n which are less than 6, which is same as saying fourth power is less than 1000, and which are greater than or equal to 4, which are same as saying fifth power is strictly greater than 1000. Thus, the possible values of n are 4 and 5. Now, the answer to the question is immediate. What are all the sum of possible values of n? The required sum is 9. 4 and 5 are the possible values, therefore, the required sum is 9. Here you have your next problem. Sum of first 12 terms of a GP is equal to sum of first 14 terms of same GP. First 12 terms sum and first 14 terms sum are the same. Given that sum of first 17 terms is 92, what is the third term in the GP? The question concerns basically on sum of n terms of a GP. Let us solve it. Recall that Sn is used as a standard notation for sum of n terms of a P or GP. So, what is given to us is S12 is equal to S14, sum of first 12 terms equal to sum of first 14 terms, but S14 is S12 plus sum of first 12 term plus 13th term, which I write as T13 plus T14. That gives S12 equal to S12 plus 13th term plus 14th term. That is 13th term plus 14th term is equal to 0. Since it is a GP, 14th term will be constant multiple of 13th term, where that constant is called common ratio. That is T13 plus RT13 equal to 0, which amounts to T13 times 1 plus R equal to 0. That is T13 equal to 0 or R equal to minus 1. If T13 is 0, the 13th term is 0 in a GP, all other terms will be 0. I mean 14th, 15th, every term will be 0, because it is obtained by multiplying 13th term with R, R square and so on. So, once 13th term is 0, all other successive terms will be 0. In that case, the sum of first 17 terms would be same as sum of first 13 terms. which is same as sum of first 12 terms and so on. Since T13 equal to 0 gives all terms to be 0, this case is ruled out and we are left with r is equal to minus 1. Thus, we observe that the GP that we are concerned about has common ratio minus 1. Let the first term be A. Then geometric progression would be A, AR, AR square and so on, which would be A minus A minus A and so on. Thus, our GP reduces to this simple form A minus A minus A and so on. Alternatively, positive and negative. Therefore, sum of n terms of this GP would be same as adding A and minus A several times. So, it will be 0 if n is even, each A will cancel with minus A if n is even. In case n is odd, each A will cancel with minus A, but we will be left with the last A giving sum to be A. So, our observation is that sum of n terms of this particular GP would be 0 if n is even and A if n is odd. Given sum of first 17 terms is 92. Sum of first 17 terms is equal to 92. First n terms, when n is odd, sum would be A. Since 17 is odd, we have A equal to 92. The first term of our geometric progression is 92 and common ratio we already got as minus 1. Therefore, third term would be 92. Let us proceed with the next problem. This next problem reads as follows. The sum of first 25 terms of an arithmetic progression is 525 and the sum of next 25 terms is 725. What is the common difference of this AP? This problem concerns sum of n terms of an AP. Let us try to solve this problem. Let T1, T2, etc., T25, T26, etc., T50, etc., be the terms of given arithmetic progression. Next, let us translate the information given in the question in symbol. Given that sum of first 25 terms denoted S25 is 525. Recall that we have a ready-made formula for sum of first n terms of an arithmetic progression. Further, it is given that sum of next 25 terms, which we denote as K25, to be 725. That is K25, which is equal to T26 plus T27 plus etc. up to T50 is given to be 725. Let me remind you that we don't have a ready-made formula to find sum of terms of an AP starting from 26th term and ending with 50th term. However, let us proceed as follows. Recall that 26th term T26 will be given by first term plus 25 into common difference. Similarly, 27th term in notation T27 is given by first term plus 26D. With the intention of connecting K25, namely the sum of next 25 terms of the AP with S25, namely sum of first 25 terms of the same AP, let us do the following. The 27th term I can write as T1 plus D plus 25D. 26D is being simply decomposed into D plus 25D. From this, one can observe that 27th term is second term plus 25D. In a similar fashion, 28th term, which is given by the formula first term plus 27D, can be rewritten as first term plus 2D plus 25D. Now, observe that T1 plus 2D is third term. Therefore, 28th term T28 can be written as third term T3 plus 25D. Proceeding like this, the 50th term T50 can be written as 25th term T25 plus 25D. Using this, let us write expression for K25. K25, which is equal to sum of T26, T27 up to T50, can be written as T1 plus 25D plus T2 plus 25D and so on T25 plus 25D. Let us regroup this as T1 plus T2 plus etc. up to T25 plus 25D plus 25D plus etc. 25D. There are 25 such terms. From this, one can gather that K25 is equal to sum of first 25 terms, that is S25 plus 25 times 25D. From this, D can be isolated as follows: D equal to K25 minus S25 by 625. Substituting the value of given K25 and S25, we obtain D equal to 725 minus 525 by 625. With simple calculation, D reduces to 200 by 625, which can be written as 8 by 25. Thus, the common difference of given arithmetic progression is 8 by 25. We shall conclude this lecture with this problem. We shall continue to explore more problems in coming lectures. Thank you.